Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on electricity and magnetism. We have been discussing about the concepts related to electrostatics in this part of the lecture series. In today's lecture, we are going to learn about the concept of capacitance. In this lecture, we are going to see the definition of capacitance and then the unit of capacitance, the principle of capacitors and the capacitance of capacitors for spherical, cylindrical and parallel plate capacitors. So, the entire lecture is devoted to the concept of capacitance. First, I would like to give the importance of the terminologies. The capacitance we say sometimes and capacitor we say. What is the meaning of this? Capacitance is the property, right? It is the property. Capacitor is the device which uses the concept of capacitance. So, hereafter we will have to be little careful about the terminologies. Capacitance, when we say, it is the property of a conductor or the arrangement. Capacitor is the physical tangible one, which is the device. We will see what is the capacitance, what is the property. We will get the definition of capacitance and then slowly move on to how to fabricate the capacitors and what about the expressions for the capacitance of capacitors and so on. Let us see the definition for capacitance. Capacitance is the ability of a conductor to store charge. In simple terms, when we say when charge is stored on anything, it has got the capacity to store, right. Then how much charge that can be kept? Is there any condition for that? So, more is the number of charge or more is the charge that is on a conductor, more is its capacitance. Like that we have a kind of misunderstanding, but it is not actually the amount of charge that is deciding the capacitance, it is the ratio. So, we will have to learn the technical definition of the capacitance. If a conductor acquires a charge q, its potential increases by an amount V, or we can say because of the charge q it would have the potential V. So, these two are the quantities inevitable. For a particular charge q, there is a potential associated as far as the conductor is concerned on which the charge is kept, right. So, these two are the two quantities inevitable. Because of the charge there is a potential, right. Now, what is capacitance? For a conductor, the ratio q divided by V is independent of q and depends only on the geometry and the permittivity of the conductor. As far as the ratio is concerned, what is the ratio? The q divided by V, this quantity is independent of q. How do we say it is independent of q? Let us have a look at this. If we increase the charge q, will it not increase the potential also? This also will rise, right. So, as q increases, as we try to keep adding the charge on the conductor, its potential is also likely to rise accordingly. So, this ratio will remain constant, it depends but on the geometry and the surrounding in which it is kept, which is called the permittivity, the electrostatic property. How it depends on the geometry and the permittivity we will be learning in this lecture. The entire lecture is devoted for that only. This ratio, which is represented as Q divided by V, is called the capacitance of the conductor and is denoted by the letter C. So, the learning is the ratio Q divided by V is called the capacitance of a conductor. It may be a conductor or it could be an insulator also. If we have the charge on the insulator, it would be the capacitance of the insulator, right. This is the concept. Let us see what do we have further. The unit of capacitance. The capacitance of a capacitor is defined as the ratio of charge on the conductor to its potential, which is shown here as the expression. The capacitance is also defined as the amount of charge given to increase the potential by unity. This also is one definition. If we increase the potential by 1 volt, how much of charge we need to have? The delta Q divided by delta V, the change, that also could be used, and it is represented as the term farad in honor of the great scientist Faraday, Michael Faraday, right. But the quantity represents the capacitance. The letter is capital F, F represents the farad, but when you write it in farad as full form, it should have a small letter in the beginning. The practical units of the capacitance are not the full farad, but it is microfarad and picofarad. 1 microfarad is 10 to the power minus 6 farad and 1 picofarad is equal to 10 to the power minus 12 farad. Why do we have the microfarad and picofarad as the practical units? See, when we say 1 coulomb of charge, it has got large amount of elementary charges. What is an elementary charge? It is a charge of an electron. In one of the lectures we have come across this concept. To form 1 coulomb of charge, some 10 to the power 18 number of electrons, no, huge number it is, that number is required. So, the practical unit for the capacitance is lesser than the farad that we have defined. See, what is farad? It is 1 coulomb divided by 1 volt, then we say the unit is 1 farad, right, but the charge is a huge charge. So, that is why we have the smaller units microfarad and picofarad as the practical units as far as the capacitance is concerned. Now, we have the principle of capacitor. What is the principle? How do we store charge on the capacitor? Let us see the concepts here. Consider an isolated and insulated metallic plate A. This is a plate. Do not give importance to the other arrangements. As we discuss, the other arrangements come into the picture, but now consider only the isolated plate which is insulated also. Let the charge on it be Q and its potential V. Thus, its capacitance is Q divided by V. Let another insulated metal plate B be kept near A. So, this is an isolated charge which is given the positive charge. Keep this in mind, this positive charge is placed on it. It is not due to induction or anything. We purposely place the positive charge on the plate A. Now, we keep another insulated plate B here, which is neutral. We do not have any charge, but because of the induction, this side the negative charges will appear because this positive charge will attract them, and this side will have the positive charge, right. This is due to induction. What is the main charge? This A, charge on the A is the main charge. Now, if we connect the plate B this side to the earth, the positive charges will go to the earth and this has got the induced charge appearing on it. If you remove the earth connection, what will happen? The plate B will have the negative charge on it. So, this arrangement is the main basis for the capacitance. Now, if you have a look at this, here we have a positive plate and here we have the negative plate. This negative charge is due to induction. Together what is the charge? The net charge is 0. We can consider it in one way, the electrons from the A are replaced or pulled out and kept on the plate B. Thus, the neutrality is also maintained. So, this combination, the positive and negative plate together is called the capacitor arrangement. Now, why do we have to have the two plates A and B? Can't we have the A plate alone as a capacitor? Yeah, it is possible. One isolated sheet can act as a capacitor, one single conductor or one single charged object, that also can act as a capacitor. But why do we always have a oppositely charged, the negatively charged plate also near a positive plate, and together we call that as capacitor, right? We are going to have an explanation to that. Equal amounts of negative charge are induced on B nearer to A and the positive charges on the outer side of B. The induced negative charges decrease the potential of A, whereas the induced positive charge increase the potential of A. Since the induced negative charges are nearer to A than the positive charges, the overall potential of A decreases. Thus, the capacitance of A increases. The positive charge on A can be neutralized by connecting it to the earth. Thus, the capacitors consist of two conductors charged opposite. What is the concept? Have a look at this. If we have this as the positive charge, and what about the potential? Its potential is V. Placing a negatively charged plate, will it not reduce the potential of A? So, once V alone is reduced, the capacitance will increase. So, that is the concept. That is why we always have a negative plate nearer to a positive plate, so that the together they form a capacitor. And again the charge neutrality is also maintained. Whenever a plate is charged positive, there is a negative charged plate. So, the neutrality condition is also maintained. And one more point, when we say the charge Q, that is on the capacitor arrangement, we always consider the positive charge, right, the positive charge that is placed on the positive conductor, that alone is taken as the term. See, have a look at this expression. This Q is the charge that is on the charged plate A, this alone appears here. What about the total charge? Total charge is 0, because we have equal negative charge here. Then we should not argue that the net charge on the capacitor is 0. It is always considered the positive charge. We can have the negative charge also in the expression, but any one charge is always considered. Negative charge means we should not put minus sign for it, because capacitance is always a positive quantity. We keep the positive charge in mind and do the discussion. Let us see the concept of spherical capacitor. Let two concentric spheres of radii A and B be considered. The inner is charged with plus Q and the outer is earthed. See, these are the two spheres. We have a positive sphere here whose radius is A, and the other sphere which is concentric, and that is connected to the earth. What will happen? Because of the positive charge, there will be induction happening, the negative charge will be there, positive charge is given to the earth by connecting the earth connection. So, what is the electric field between them? This is the expression for the electric field, which is the sphere will act as a point charge concentrated at the center. Keeping that in mind, we have done this. This is the expression for potential. These are all very familiar equations for us, and E dot dl is expanded in the scalar form, and we have a minus sign appearing because the angle between E and dl, here all are marked. Electric field is appearing from positive to negative, and dl is taken in the opposite direction. So, we want to measure it from the positive sphere to the negative sphere. So, we always use the term r. So, this is the expression for the potential which could be calculated here. So, when we do the integration from B to A, where are the B and A? See, we always move in the opposite direction to this A. So, we have to move it from B to the point A, which are the radii eventually, and the integration is performed, and we have the limits applied here, upper limit and lower limit, and we have this as the final expression for the capacitance. How do we say this is capacitance? We have already defined the capacitance as the ratio between the Q and V. So, that is appearing in the expression. Here we have Q and the original expression is for V. So, Q divided by V, when we simplify, that is simply taken as the capacitance. So, this is the expression for the capacitance for concentric spheres. The above expression shows C depends only on the geometry of the conductor and the permittivity of the medium. See, A and B are the radii and 4 pi is the number numerical and epsilon is the permittivity. So, that is why originally it was mentioned the capacitance depends only on the geometry and the permittivity. If we take the B to infinity, what does that mean? We have an isolated sphere. If we take this B to be infinity, that means we do not have this negatively charged sphere at all, it is taken to the infinity. Then what will happen? Put B as infinity. So, the equation becomes C is equal to 4 pi epsilon naught A. Here we have to put, not in this expression, in this expression when we put B as infinity, 1 divided by infinity becomes 0, only the term A appears. So, when we simplify, we get this expression as the expression for the capacitance of an isolated conducting sphere. I have mentioned even a isolated sphere can act as a capacitor. So, here is the proof, this isolated sphere can also act as a capacitor. So, what is the equation for the capacitance? It depends on the radius of the capacitance A and the epsilon naught value, which is the permittivity. So, though we define the capacitance as the ratio between the charge and the potential V, the final expression that we obtain the expression has only the geometrical term and the permittivity term. So, that is why we conclude that the capacitance depends on the geometry and the permittivity. Once again, I would like to explain about the isolated sphere and its capacitance. Have a look at this. Here the term A appears, right. So, how do we increase this C, the capacitance? By increasing this A. So, as A is increased, capacitance will also increase. So, it depends on the size. Larger the radius, larger is its capacitance. So, if you want to have a capacitance as a high value for a sphere, we need to have a large sphere with greater radius, right. And also this epsilon naught, if it is kept in free space, we will have only epsilon naught. If it is kept in a medium, we will have the one more term appearing here, which is the dielectric constant, right. I would like to mark that as K here. We will have one term K. What is K? Dielectric constant. So, that also will increase the capacitance K times. So, if we have dielectric material in a capacitor, that will increase the capacitance. Depends on the size and also the dielectric that we use in the medium. We will go ahead with the discussion for the other case where the inner sphere is earthed. Let us see. This is also one easy term. The inner sphere is earthed. I would like to explain the arrangement. We have the concentric spheres, the outer sphere and the inner sphere in the same manner, but the inner sphere is somehow earthed. We do not have electrical contact here. We have the inner sphere connected to the earth. Now, what will happen? Let the inner sphere be earthed, the charge plus q is given to the outer sphere, and plus q is distributed as plus q1 and q2 on the inner and outer surfaces respectively for the outer sphere, that we should keep in mind. Its total charge is q, inside it is plus q1, outside it is plus q2. So, q1 plus q2 will always yield q, and because of this plus q1 here in the inner, there is a minus q1 appearing due to induction, and as it is connected to the earth, the positive charge which is there, that is connected to the earth, it is removed. The charge plus q1 on the inner surface of the outer sphere induces minus q on the outer surface of the inner sphere. So, the charge plus q1 on the inner sphere leaks to the earth, it does not have the positive charge that is connected to the earth. So, this is the arrangement due to induction. How do we do the calculation? The two spheres now behave as two capacitors connected in parallel, one outer surface, outer sphere and the inner sphere, these two are connected in parallel because of the same potential that is existing throughout the inner arrangement. So, what will happen? Inner sphere of radius a and inner surface of outer sphere form a capacitor of capacitance C1. The outer surface of the outer sphere and the earth form the capacitor of capacitance C2. There are two capacitors. Have a look at the arrangement. These two, plus q1 and minus q1, this is one capacitance. The other capacitor is the plus q2 and the earth which is connected, the inner one is connected to the earth. So, that those two conductors act as one set. What about the capacitance of each set? The C1 is for the inner and outer, right, which is a known expression for us, and C2 is an isolated one which has got only the outer sphere whose radius is b, it is an isolated sphere. So, these two are connected in parallel. So, this is the equation for two capacitors connected in parallel, C1 and C2 are connected in parallel. So, we just add them to get this as the final expression for the arrangement. So, considering the arrangement of conductors in concentric spheres as far as this explanation is concerned, we can find out the capacitance of spheres, isolated sphere or even concentric arrangement. Now, we will take up another case of cylinders. We will do it for a cylinder. The approach is the same. So, I would like to quickly run through except for the equation for the electric field, otherwise the calculations are same. Have a look at this. Let us consider two concentric cylinders arranged to form a capacitor. The inner one has got radius a, outer one has got radius b, and inner one is given a charge plus q, outer one has got charge minus q, the outer one is earthed. So, this is a cross sectional view of the arrangement. This is actually a cylindrical one, right, it is a cross sectional view. So, electric field is from positive to negative, we move from the negative to positive sphere, from B to A we have to move. What about the electric field that is existing between them? So, this is the known expression for us, the electric field due to a cylinder may be a line charge. So, this is the expression, lambda is the linear charge density. So, it is q divided by L. We write the expression for potential, the minus sign appears by the formulation itself. The integration is done from B to A, we expand E dot dl here like this, all are known methodology only. So, the same trend we follow, and here the integral dr by r comes. So, which has got the natural log r as the integral value of it. So, we apply the limits, finally, we get the expression for C as q divided by V. We have to rewrite this equation for q divided by V and call that as C, and this is the final expression for the capacitance. It depends on again geometry, L is the length and B and A are the radii, this is the natural log here. So, it depends on the geometry and the permittivity alone. This is for the cylindrical capacitors. Now, we are going to move on to a very important arrangement, which is the parallel plate capacitor. we will take up that for discussion. Parallel plate capacitor consists of two parallel metal plates of area A and separated by a distance d. One plate is given charge plus q and the other minus q. This might be due to induction and the process I do not want to discuss further. So that the charge density on each plate is plus sigma and minus sigma. They are the charge densities on them. I have shown only the charges and charge density as sigma. How the electric field will exist? It is from positive plate to the negative plate. So, we need to move against the electric field as far as the calculations are concerned. So, that is marked as dl here. The distance of separation for the two plates is d. Now, what about the formulation? We need to find out the electric field that is existing between the plates and then go ahead with the integration. We will do it this way. We know from the applications of Gauss law that the electric field between the plates is given by this expression E is equal to sigma by epsilon naught. This is a known expression. Sigma is the surface charge density, which is expanded as q divided by A. The usual formulation is done. We integrate it from the distance d to 0 to move from negative plate to positive plate. Once again the E dot dl is expanded like this and the usual integration is performed and we finally rewrite the expression for q divided by V, which is C, and we have C is equal to epsilon naught A divided by D. What is A? A is the area of the capacitor plate, and what about D? D is the distance of separation. Epsilon naught is the permittivity, and if you want to increase the capacitor of the parallel plate capacitor, we need to increase A and decrease D, and also introduce a dielectric material which will have a positive value K here, so that the capacitance of the parallel plate capacitor is increased. So, we have got the expression for parallel plate capacitor also, which is a very important expression. Actually, how do these capacitors appear in electrical circuits? We have got several shapes. Three important shapes today we have seen. One is a spherical capacitor and another one is a cylindrical, and now we have seen parallel plate capacitor. In electrical circuits, they appear in different shapes and different colors. Let us have a look at the capacitors used in electrical circuits. This is a cylindrical capacitor. These are all parallel plate capacitors. It has got two plates kept parallelly inside. The two leads are shown, and these capacitors are called variable capacitors. We can rotate a knob and change the capacitance itself. How it is done? See, we have the different set of plates like this. When by rotating a knob, the area of overlapping will vary. The area, if you rotate it like this, the area is less, the overlapping area is less. If you rotate it inwards, the overlapping area is more. So, thus the capacitance can be increased or decreased based on varying the overlapping area, and also the distance between the two plates also could be varied by rotating the knobs. Mechanical arrangements could be made. These capacitors play vital role in electrical circuits. They are used to conduct alternating currents and block DC currents and store charge. It has got lots and lots of functionalities as far as electrical and electronic circuits are concerned. We will learn about the role of dielectrics in capacitors. We need to learn elaborately about it because that is included in our curriculum. We will do it in the subsequent lectures. So, I think we can summarize what we have learnt in this lecture. In this session, we have seen the definition of capacitance, unit of capacitance, the principle of capacitors, capacitance of capacitors for spherical, cylindrical and parallel plate capacitors, and also the various shapes of capacitors and how they are connected in electrical circuits. Before we wind up this lecture, let us test our understanding by answering these questions. Define capacitance and mention its unit. Give the principle of capacitance and discuss why two conductors are preferred to form a capacitor. Derive the expression for capacitance of a spherical capacitor. Derive the expression for capacitance of a cylindrical capacitor. Derive the expression for capacitance of a parallel plate capacitor. See you in other lectures with much more concepts related to electrostatics. Thank you for watching this program.